Hey science guys, we're about to do some friction. Not much friction on this board, but we're going to talk about how to find the coefficient of static and kinetic friction as a box slides down a ramp. Oh boy, this is actually a complicated scenario. It is not your typical friction scenario, but let's start with a typical scenario. If we have a flat surface and we have a box and it's moving, okay, now here's the trick of friction. If you know if something's accelerating this way, so there's a force on it, that if there's friction, it's always in the opposite direction of a force. It's never with the force. Friction's never helping you, it's always working against you. Air resistance, if I'm flying through the air, or falling through the air, I don't fly very often, if I'm falling through the air resistance is slowing me down. It's going the opposite way. It's never helping me. It's never pushing me forward. That's wind. That's a whole different thing. But air resistance doesn't do that. So anyway, friction. Well, what is friction usually based on? Well, it depends on what this is made out of, right? Sandpaper, concrete, and things like that are going to have a very different friction than, let's say, this whiteboard, a piece of glass, a piece of ice, right? So we have to compensate for that using a number, you know, because this is physics and we do numbers. And we call it a coefficient, meaning if you know anything about coefficients, it goes out in front of something, right? So let's look at friction real fast. Friction, okay, little fancy F there for friction, so we don't mix it up with the other forces. We've got to put vectors on our forces. This is also a vector because it has a direction. Put a little arrow in there. Friction is based on that coefficient and one of my favorite Greek letters called mu. Not Mewtwo, we're not talking Pokemon here, we're talking mu, which is this number. Traditionally, if I was an engineer, there might be some book out there or some database online. No one uses books anymore. This database online that would tell me what this number is. And it's different for everything. If you look at my hand here, and I rub it across this table, the coefficient of friction isn't just based on the table, and it's not just based on my hand. It would be the coefficient of friction between skin and oak. This is not oak, but oak, we'll say. Or the coefficient of friction between plastic and plastic, right? The coefficient of friction between the rubber of a car tire, the vulcanized rubber, and concrete or asphalt, right? So this number is found experimentally and recorded. Now, I believe just recently I was watching another video where they talked about this, and they said that the coefficient of friction only goes out to 2 digits. So let's say the coefficient of friction ends up being 0.27. And why was that? Why is it only 2 digits? Well, it turns out it's only 2 digits because if you go any farther than that, what ends up happening is this, well, let's say I drop this block down another block here, and I let it slide, okay? If I were to measure the coefficient of friction, the friction right here is actually different than the friction here, and different than friction here, and even here. Every part of it's different. Every part of this structure is different. It's not that different, but it's different enough that you can't go beyond this for the coefficient. Anything beyond that is meaningless because almost every substance changes a little bit with its coefficient changes. Now, once again, there are 2 types of friction. There's 2 types we're going to deal with. There's rolling friction, we'll talk about that a little bit later, which is basically static friction. But we have static friction, which is how hard it is to get something started moving. So I'm pushing on my hand right now, and it's not moving, 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 it moved. We broke the static friction. Sorry guys, it returns. It's dead. It's broken. Okay, static friction, how hard it is to move something. Okay, that's what that friction, I'll put an S right here, static stands for. Okay, if we're dealing with friction, by the way, this is friction. This is just the coefficient. Okay, and this is not all we got to worry about. There's one more piece we're going to talk about. The static friction. Kinetic friction, well, that's how much it gets slowed down while it's moving. Okay, you might have already guessed this, but this one is going to be a higher number than this one. This one's going to mess you up a bit more than this one. And the reason is, at least what I've been told in time, is as you place two objects against each other, little tiny static bonds form between those objects. You can't see them. They're like super small. But basically, because those static bonds form, to get something moving, you have to break those bonds. That is a lot easier than kinetic friction, which is where those bonds are trying to reattach themselves. Static bonds are trying to reform. Of course, that's not it. It also has to do with, like, look at the surface. It's got bumps all over it. The grooves in my fingers are going to get caught in them. Things like that. Okay, but that's the explanation. This is always higher than this, as far as I know, unless there's some circumstance I've never heard of. I mean, it's possible that there is one, but that. Now, what's the second thing that'll affect friction? Well, there's a difference between me sliding this on the surface and me sliding this on the surface while putting weight on it. So, the weight of an object, the weight on an object, or the force on an object, let's not use the word weight here, affects the static friction and the kinetic friction in general. So, how can we identify that weight? Well, in this case, we would say, if I just push this along, we'd say it's based on gravity and mass. So the weight, literally the weight, mass times gravity. But what if I was pushing it against the wall and sliding it down? It is no longer based on gravity. We can't use the same definition down there as we used up here. It's now based on the force of my hand against the wall. And it's like, well, how can we make this work for both scenarios? What if we just say it's the force coming out of the surface, the equal and opposite force, the Newton's third law force? Okay, and if you remember what we call that surface force, that perpendicular or normal force, is the normal force. We multiply that by n. Okay, n makes some people uncomfortable. So instead of saying n, sometimes we'll say f of g. But I don't like to use f of g, like I said, because if we're using the wall, gravity doesn't work. So we'll just stick with n for normal force. Because normal force is just any force that's due to a force being pushed, right? It's the pushback. It's that what we call a third law pair. My hands, the first part, the pair to that is the wall pushing back. That would be the normal force, and that affects the friction. All right, cool. So we have a definition for friction. Okay, let's use it in a complicated scenario. This is too simple. My force is that way, my frictional force is that way. If I were to draw an FBD, free body diagram, I would say that we have the force of gravity, F of g. If we have the force of gravity down, Newton's third law says we've got to have the normal force up. So I'll say F of n, normal force. Also, this thing is being pushed forward. Let's say I'm pushing it with my hands. So we have a force going that way. I'll do F of A. Oftentimes you'll see F of A, that just means force applied. It means whatever you're putting into it. And then the opposite of motion, the direction of motion, is that frictional force. And because it's moving, we'll say it's F of K. Okay, now, if you noticed, I made F of K shorter than F of A. If it wasn't shorter, it wouldn't be moving, right? This actually represents what's happening. And once again, once you draw this, then it's really easy to sit there and say, the sum of the forces equals the sum of the forces in the x plus the sum of the forces in the y. We're dealing with 2 dimensions. 3-dimensional, we'd say z. Let's say we lived in the 4th dimension, we'd say z and, I don't know, q or something. But we don't. We stop at 2 dimensions and there's little in physics. And then we say, well, what is that? Well, the sum of the forces in the x equals force applied minus frictional force. And the reason it's minus, they're in opposite directions. Also, the sum of the forces in the y is equal to the normal force, I like to keep gravity negative because it's down, minus the force of gravity. And if we calculate, and this is the point where we can start doing calculations. So in a lot of physics problems, they want to see the drawing unless they give you one. They want to see the free body diagram, and then they want you to see to break up the analysis of it. Now, let's give you the real problem. Now that I've given you this full, lengthy background, I promised Colby this would be short, but I threw in a little, I threw in this basic lesson here on friction because I don't want anyone to be confused when I jump into a more complicated problem. Okay, so what we're going to do with the ramp now. Keep these definitions in mind. They work either way. First, let's deal with static friction. Let's say the box isn't moving. Now, what I had students do, some of you are my students, is instead of just putting a box on a ramp, they put a textbook on a board, and they lift that board, and they take their cell phones, and which I don't have, but they take their cell phones, and they look at the angle, because you can download an accelerometer app that tells you the angle, or gyroscope app that tells you the angle you're at. And they lift it up, lift it, until they get an angle. And how do they know they got the right angle? As soon as it starts to slide, they know that this friction is as high as it can get. That's static friction. Because think about it, as we're lifting it and lifting and lifting it, gravity's pulling it down more and more and more. But static friction is still, if static friction is still preventing it, static friction is going higher and higher and higher to counteract that, right? Now, as soon as that breaks and it starts to slide, immediately we switch over to kinetic friction. We do the jump to the kinetic friction because now we're worried about what it's doing as it's moving. Okay, and then we can solve some other physics problems like, oh, what did it do when it launched off the end and crashed into a ravine, and that's kinematics. But, so, let's look at this thing. First scenario, not moving. Okay, well, let's just come up with an angle. Let's say, I don't know, 20 degrees. It starts to slide, so that tells me something. And the mass of the box, I don't know. Let's say 10 kilograms. That's a nice, safe number. Okay, so let's draw a free body diagram. All right, well, what's pulling the box down the ramp? Well, gravity. No one's pushing it. It's not actually moving down the ramp, but is there something pulling it down? Yeah, gravity. And I'll draw gravity that way. No, don't let me do that. I did that on purpose. Gravity always points towards the center of the earth. It points down. This downward gravity is pulling this diagonally down the ramp. Now, I will later on break gravity apart and say, oh, some part of it's going this way. But I'm not going to do that until I draw the FBD. I want everything out on the table before I'm done. Okay, what other forces do we have? Well, am I pushing this down the ramp? No. We're letting gravity do that for us. So no more downward ones. Well, we have the frictional force, which is in the opposite direction. I'm going to draw it up here as well, which is in the opposite direction as the way it would be moving. And remember, that is, what type of friction is that? That's static friction. And I'm using the wrong F again. Static friction. Okay, and this is F of G, force of gravity. All right, finally, do we have any other forces? Well, we have the normal force, right? Because if not, this would be falling through the ramp. Now, remember, the normal force is not the opposite of the force of gravity. It is the opposite. It is perpendicular to the surface it's leaning against. So it's actually coming out of the triangle, right? It's coming out this way, and we'll call that F of N. Now, why do I want to know the normal force? Well, I draw it because it's proper, but also I'm going to need the normal force, if you remember, to figure out what friction is. All right, so let's figure out how this works. Well, this is the hardest part of these problems. Up until now, you've been taught that horizontal is cosine and vertical is sine. The more, and let's say we take an angle, the more cosine it is, the more closer it is to horizontal, and the more sine it is, the more closer it is to vertical. This ramp problem throws that logic out. Well, it doesn't throw it out the window. It's still the same logic. But we have to start thinking upside down to do this one, and I hate that. This is why. I'm going to switch colors. This will make it a little easier. We actually are going to start looking down the ramp. Now, there is a reason for it. It does have to, the reason we look down the ramp is we're going to take this triangle and we're going to make this triangle in here. I'm not going to do that right now because it takes a lot of work, and it's just going to confuse people. But trust me, we're going to look down the ramp and we're going to say, okay, the component of gravity that has to do with the forward motion is this way. And the component of gravity that has to do with the normal force, the part that's pulling down in the opposite direction of the normal force, is in fact this way. So this is actually, we can split this into these two pieces. Now, here's the confusing part. If we look at this right here, right, this upward direction is up the ramp. This is actually the sine of theta. And this is actually our horizontal, and this is the cosine of theta. Okay, our first instinct might be to say, well, going down the ramp seems kind of sideways, so that should be cosine. No, it's also sine, right? It's in this plane. So, how do we figure this out? Well, first of all, we've drawn our FBD. We've drawn our free body diagram, right? We have our FBD. How do we want to do this? Well, what do we do every time we have an FBD in every other scenario? Well, we have to sum the forces. Well, right off the bat, before I even write one thing on the board, I'm going to say, is the box moving? No, it's a drawing. It's not going to move. But in our pretend scenario, the box also isn't accelerating. See, moving is the bad word to use. Is it accelerating? No, it's not changing direction. It's not changing speed. It's not getting faster or slower. Therefore, the sum of the forces equals the sum of the forces in the x plus the sum of the forces in the y. And guess what? They all equal 0. They have to equal 0. Okay, well, let's just focus on one piece of them. What's the sum of the forces in the x? You know, I'm using x. I don't like to use x because we're now working in this sort of imaginary new plane. How about instead of x, we say, because now x is suddenly coming out, right? We'll say force perpendicular. And we'll say this force, because it goes along it, is the force parallel. That way we're not getting confused. Well, x is sideways. No, perpendicular to the ramp and parallel to the ramp. That simplifies things a little bit. Okay, so sum of the forces in the perpendicular equal, well, what are they? Well, we have the normal force. Force normal. And we have some component of gravity, right? There's some component of gravity. So we have plus, well, what component is it? It's coming down this way. And remember, this is now our y, and this is our x. So it's going to be the sine. So force of gravity times the sine of theta, which in this case is 20 degrees. But we'll solve that later. Okay, what about the sum of the forces in the parallel, going with the plane? Well, and by the way, we know that this equals 0, right? Because this one's not moving. In the parallel, well, we have the force of friction, the frictional force, static, and we know that we have the downward force. Well, the down's going to be, we'll call the downward force, by the way, I'm going to call this one negative. We're going to call the downward force negative as well. And because down's the opposite of up, and I wanted friction to be positive here, and you'll see why in a minute. Okay, so friction's not the frictional force, and this other force is in that cosine plane, right? So we're going to say minus f of g. Ooh, I did that backwards, didn't I? No, f of g. My bad. But go back one. Remember I said it's backwards. Cosine theta. See, I'm getting confused by it too. Sine of theta. Okay, and we know that those also have to equal 0. Now, let's focus on this one. This is the one we're trying to solve for. I want us to figure out what that friction is, or at least what the coefficient is. All right. So because this plus a negative this equals 0, this also means that the frictional force plus, or frictional force equals, we'll move that over there, f of g times the sine of theta. Cool. Well, let's get rid of f of g. Let's make f of g mg. We know what that means, mass times gravity. That's the same thing as force of gravity. Now, the frictional force. What is the frictional force? The frictional force is, remember, mu of s, well, let's replace it with that, mu static times the normal force. Where's the normal force? There's the normal force. What is the normal force? Well, let's find out. It's coming out of the plane. It's the opposite. It's equal and opposite to that portion of gravity. It's pointing out. Well, what's that portion of gravity called again? Well, that's mu of s. It's force of gravity times force of because it's mu times n, times force of gravity times the cosine of theta. Remember, force of gravity is the same thing as mg. Okay, well, what can we do here? Well, we can start to simplify. We have mass times gravity on this side. We have mass times gravity on this side. When you have something on two sides, they cancel out. Bada bing, bada boom. Okay, what do we have now? Well, mu s cosine theta equals sine theta. Well, we're trying to figure out what this is, so I'm going to move cosine theta over there. Sine theta. Well, something really spectacular just happened here, right? We got rid of all the other parts. We have no forces, we have no nothing. And if you guys know your trigonometry, sine of theta divided by cosine of theta is equal to always tan of theta. So if I want to know the static friction on that object, I'm going to lift that board, and as soon as I hit that angle that it starts to moving, I just plug tan of theta in my calculator. Let's see what it is. Well, tan of theta, which is 20 degrees in this scenario, gives me 0.36. Okay, I don't know what the material is, I just made up this problem. But let's say I did a book and a piece of wood, and this is what I got. I'd be like, every time I use a book and piece of wood, I'm going to get the static coefficient is 0.36. Cool. Okay, what's that tell us about the friction? Well, we'll go back to the normal force, or the frictional force. Where are you? Which is this right here, 0.36, and multiply that by the normal force. What was the normal force? The normal force was the cosine of that angle, 20, times mass times gravity, times the gravitational force, which is 9.81 times 10, because remember it weighs 10 kilograms. Gives us, well, we have a friction of 33.55 newtons. That is slowing us down by that much. Okay, really, I did this problem to solve for this, but I just want to show you that it's usable. I can now use that value that I got to figure out what the actual friction was. Don't get this confused. This value is not the friction. It is the coefficient of friction with that surface, and you can save that number once you figure it out. Okay, now that we've covered this one, let's cover the moving box real quick here, because we all love the moving box. And I'm going to leave all this up. This all remains the same. Nothing else changes. Let's say the box starts to move down the ramp, and it accelerates, right? If it accelerates, we now have a force applied. We have a force down the ramp. Okay, let's see what that is. And by the way, we're not pushing, so let's not draw that in there. Our FBD is going to be the same. We're going to have a frictional force back. We're going to have a normal force pointing out of the ramp. And we're going to have a gravitational force pointing down. And I'll just write this as f of g. This is friction, but now we're doing kinetic friction. And this is force normal. perpendicular force. All right, and we know it's moving. Well, sum of the forces, again, sum of the forces equals sum of the forces in the x plus the sum of the forces in the y. Sum of the forces, and remember I didn't want to do x and y, so we said perpendicular and parallel, which is sort of opposite what we're used to. Normally x is parallel. In this case, our y is perpendicular, is parallel. And you remember we proved that before. Okay, so sum of the forces perpendicular is equal to, well, this is going to change. Is it going to change? No, not going to change. Same thing. Perpendicular is, that's the back and forth, is going to be m, well, it's going to be this, right? It's going to be the force of gravity down, which is mg, okay, it's perpendicular, so it's sine of theta. Oh, wait, nope. It's backwards, remember, cosine theta. And that is down, that's negative. And we're going to add that to the opposite, which is the normal force. Force normal. Cool. And the sum of the forces in the parallel. This is where things are going to get weird. Okay, what was it before? Well, before it was the well, by the way, you guys know this one equals 0 because the up and down is equal. Okay, they balance out. It's not falling through the ramp or up the ramp. Okay, and remember, this is actually the angle of gravity that's exactly the opposite of our normal force there. So that's why we use that piece. But perpendicular, we're going to say, okay, we have the frictional force, K, again, and we're going to add a negative that's in the opposite direction of the force down the ramp, or the force of gravity in that direction down the ramp. Remember that area, that direction down here? That piece of this that's in that way and not in that way? That's actually perpendicular to the other one, or we say normal, but in this case we'll say perpendicular, is mg sine of theta, and it equals, well, does it equal 0? No. I said the box is going down the ramp now, right? It's sliding down the ramp. So it actually equals a force. Well, how are we going to write that force? Well, it's going to be some mass. It's going to be the same mass. That's not going to change. It's going to be the same amount. But it's going to be some new acceleration. It's going to total, these two total together is going to equal a different acceleration. I'm like, okay. We're not messing with gravity here now. We're messing with something less than gravity, right? It has to be less than gravity because friction is taking away from it, right? It has to be less than this. Okay, so let's figure out let's solve for it. Well, let's figure out what mu of k is. Friction, kinetic friction, remember, just like up there, is equal to mu of k times the normal force. Okay, well, what's the normal force? The normal force right there is coming out. So in this case, it's cosine. So it's mg cosine of theta. Not negative like this one, because it's coming out. This is actually gravity down. This is the opposing force. So mu of k times mg cosine theta. And then we're going to add that to, okay, mg sine of theta. Cool. So now we got some similar units now, and that equals ma. Let's write it out here and do a complete equation now. Okay. So we end up with mu of k times mg cosine theta plus mg sine theta. Okay. And by the way, I say plus, but it's really the opposite direction, right? Plus a minus mg sine theta, okay, because it's going down versus friction, which is going up, and that equals ma. Well, what can we get rid of that's in every part of the equation? Well, this is all multiplied, this is multiplied, and this is multiplied, and what's the same in all three of them? Well, so far it's just m. We got g in both of those, but we'll leave that there for now, and a. Now what do we got to do? Well, we'll keep that negative there. Now what we got to do is we got to get u of k by itself, because that's what we're trying to solve for. So let's move this over here. That's why I left it negative, right? Because now when we move it over there, we subtract it from both, we add it to the other side, it becomes positive. So a plus g sine of theta. Okay, what do we want to get rid of now? Well, let's get rid of g cosine of theta. Divided by g cosine of theta gives us our friction. There it is. Okay. Now, when I had students do this, they did the same thing. They held the ramp at the same height that it slid, maybe a little higher, so it slides a little faster. And what they had to do is they had to take a meter stick and a stopwatch, and they had to sit there and say, okay. And some students actually put marks on the wood as it went down, and they said, how long did it take to get to Mark 1, Mark 2, Mark 3, Mark 4? They charted that, and what they did is they said, okay, distance, or what they did is they basically figured out velocities and times, and they got the average of velocity and times to figure out what that a value was. And we all know g is gravity, 9.81, and sine, well, whatever the angle is. So this is actually the equation that works in every single scenario of sliding friction or moving friction, right? A plus g sine of theta divided by g cosine of theta. Just like in the other one, if you remember, mu of s was equal to just straight up tan of theta. Isn't it so much simpler when the forces equal 0? In this situation, the forces didn't equal 0, so everything was a bit more complicated. But yeah, so if you're in AP Physics or an advanced physics course, besides just general physics, you should be able to practice and be able to derive these equations yourself, not just memorize them. Memorization is never the trick in physics. Now, of course, if this is your first time seeing this problem, yeah, go ahead and run it through a bunch of times, memorize it. But the next time you see any problem with a ramp or a ball rolling down something or something like that, get really, really, really good at deriving these, figuring out what are the sum of the forces, what is going which way. Okay, the first thing you always want to do before you start these, once again, is to say, do I have a force? What's my net force? Is it 0? If it's 0, then I need to start with it being 0, and I can start moving things around. If it's not 0, then I make an assumption about what it is. My assumption in this situation was that it was something. It was just m times a. So those two starting points are really important. FDD and drawings, next important. And yeah, just follow the logic, sum the forces, right? And you always want to sum the perpendicular forces, say the ones in the x versus the ones in the y. Or in this situation, the one's perpendicular versus the one parallel. That'll help you solve all these kinds of problems. Anyway, that's physics. Scott's a nerd who's not wearing his lab coat, and Colby is getting a little tired.
Yeah.
Have a good night.